Hi, welcome back. We covered float carburetors last time. We're going to talk about a little bit different kind of carburetor this time, pressure carburetors. These are sort of one step between the float carburetor and the fuel injection. I don't think that we have any of these currently running in our fleet, but it is possible if you get out there in general aviation that you'll run into some of these on higher performance aircraft, 200 horsepower and above. Pressure carburetors have a couple advantages. One is that they inject the fuel after the throttle, so the fuel nozzle is up above the throttle in the airflow, which means that there's less chance of carburetor icing. The second big advantage is that they spray the fuel in under pressure, which means that we get the fuel more atomized. We don't have to rely on the vacuum caused by the venturi to draw the fuel in. We actually blast it in under pressure. The final advantage is that if you're doing aerobatics, these are more easily adapted to inverted flight. So real quickly how these work. This is a simple diagram out of your text. They work by sensing a couple different kinds of air pressure and sampling them into some chambers that are separated by a diaphragm. So the two pressure types are venturi pressure, which they obviously sample from within the venturi, and impact pressure, which is the pressure of the ram air coming into the system. This particular example that they give here is actually representing a downdraft carburetor for a change, which may have confused you in the beginning, but the air comes in up here, moves down through the throttle and then into a supercharger, which is depicted here. The impact pressure is sensed here and goes into the dark green chamber, and the venturi pressure, or suction if you will, is directed into the light green chamber. There's a rubber diaphragm between the two, and so as airflow increases, venturi pressure gets lower, impact pressure gets higher, and the diaphragm moves to the right, which pushes on this fuel valve and opens the fuel valve. So more airflow, more fuel flow. The fuel pressure is brought in at sort of a random, unregulated supply pressure, and it goes through the fuel valve and into another chamber, and that creates a closing force. There's a little diaphragm right here that provides a closing force on the fuel valve. So you end up with this balance between the opening forces that are supplied by the air and the closing forces supplied by the fuel. And then the fuel goes on down and out a discharge nozzle down here. Here's a one that you're more likely to run into, actually, the PS5. I started with the other one because it's simpler. This one is actually more the way they're shaped, and we've got an updraft carburetor this time, just like the float carburetors we used before, except notice that the discharge nozzle is indeed up here at the top after the throttle valve, so that we're in a warmer area here and it's less likely to ice up. We are sampling impact pressure here that's coming in through our air intake, and then we sample venturi pressure inside the venturi here, and it is directed back into the gray chamber. Impact pressure here is in the light blue chamber, venturi pressure in the gray chamber. That once again creates an opening force to the right on the poppet valve. That allows the fuel, which the unregulated pressure here is in purple, that allows that to flow into the regulated fuel pressure chamber, which provides the closing force. So the opening force, once again, provided by the air pressures, is balanced by the closing force provided by the increased fuel flow. And it reaches a kind of happy medium there to provide a regulated pressure across the main metering jet, and then that metered fuel pressure flows on through these channels and up into the discharge nozzle. And along the way we have an idle control, an accelerating pump to provide a little extra burst of fuel as we open the throttle, and then a shut-off valve that once it drops, as you shut the aircraft off at the end of the flight, as the fuel pressure comes down below what it would take to run the engine, it shuts it off completely, so you get a nice clean shut-off. That's all that shut-off valve does. The accelerating pump in this case is run by manifold pressure. So as you open the throttle, manifold pressure increases, and that releases this diaphragm. So the spring here pushes in on this diaphragm and shoves that little extra bit of fuel in as you open the throttle. And that's it. So they can get more complicated. This one is a PS7, and it's got automatic mixture control. Mixture control in some of these fancier ones is accomplished by allowing some of the air pressures to bleed from one side to the other. So a little bit of the impact pressure bleeds over onto the Venturi side, which means that there's less difference and therefore less opening force on the pop valve, and that leans the mixture. The automatic mixture control valve works the same way, but it is controlled by a set of bellows, and so as the aircraft climbs and descends, a certain amount of mixture controlling is done automatically. That you're probably only going to see in something like a big radial engine, a DC-3 or something like that. So pressure carburetors, the what you need to know part about how these work is it senses air and fuel pressures via a set of diaphragms, and the diaphragms open or close a pop-up valve as appropriate to the amount of air that you're bringing on board. This provides fuel to a set of metering jets under a regulated pressure. That's the basic what it is and how it works. The nozzle sprays the fuel in after the throttle, which means that we are less likely to accumulate ice, and it doesn't rely on gravity, and so you won't have to worry about pulling negative G's. Now, I'll be honest with you, if you get into an aircraft that has a pressure carburetor and you think it's a float carburetor, it'll probably run fine for you. If you just treat it the same way that you do a float carburetor, it'll be fine. Couple things to note is that because the accelerator pump is operated by manifold pressure, pumping the throttle before you crank the engine is not going to do anything because you don't have manifold vacuum yet. But other than some small little differences like that, it runs pretty much the same as your float carburetor. That brings us on to fuel injection. Fuel injection is probably the most efficient way to get the fuel into the cylinders. The type we use injects fuel at a constant flow, so it doesn't inject little pulses of it at each intake stroke. It injects a constant spray of fuel in the intake manifold right at each intake valve, so just before the air goes into the combustion chamber, we mix some fuel with it, a constant spray of fuel. So sprays fuel into the intake manifold right at each cylinder. That is one of the hottest places on the whole airplane, so you're never going to get any ice there. And in fact, fuel injected equipped aircraft often do not even have carbureted heat or heated intake air available. They have an alternate intake air, but not heated. Very even fuel distribution, since we have very carefully designed and calibrated orifices at each cylinder. When we lean the mixture, we get the exact same mixture at every cylinder, which means we can lean the engine overall to a leaner state and get better efficiency out of it. There are several different types of installations, and we're going to cover two of them here. But the big takeaway on fuel injection is that you need to know your airplane. You need to really study what the procedure is for your airplane and read the expanded procedures later on in the pilot operating handbook that describe how to start it on hot days and cold days, and be really familiar with it because it's very important. We're going to start with the type of fuel injection that we have in our fleet, which is the air-powered fuel injection. That's the way I refer to it, the Bendix RSA. And it works extremely similarly to the pressure carburetor in that we have a set of diaphragms, two of which have air going to them, impact and venturi, just like the pressure carburetor. Those supply an opening force to a ball valve instead of a poppet valve, but it's a valve nonetheless. So that provides an opening force. We've got impact pressure here, venturi pressure or suction here. That pulls up on this diaphragm, opens this valve. That allows fuel to flow out to the injectors. The fuel pressures to the blue and green chambers here are modified by our mixture control here, which is just a valve that gets open and closed, open for rich, closed for lean. And then there's a metering jet that gives an overall amount of fuel that goes through. And then the throttle valve. So the throttle, when you move the throttle, you're not only opening the throttle plate to control the air going into the engine, but you're also opening up a valve to increase the fuel flow. All that gets modified by the diaphragms, and then we end up with a very highly metered fuel pressure out in the injectors. There are only two injectors shown on this diagram, but obviously there would be 4 or 6 of them. They operate on the principle that at a specific pressure, a specific amount of fuel is going to flow through that calibrated orifice in the injector. Because of that, we can take one extra line and tap off of it and run it to a gauge in the cockpit, and it's a pressure gauge, but we can actually label it in gallons per hour or pounds per hour and have it be a fuel flow gauge, and it is based on the pressure that is in the injector system. So as pressure increases, we get an increased indication of fuel flow. Really nice to have. Great to know exactly how much fuel you're burning, because you can get a rough, actually a pretty good mixture leaning setting just by looking at the fuel flow indicator. Here's a cross section of those diaphragms that are opening the ball valve in this case. And you'll note that it's mounted right to the side of the throttle body, much again like the pressure carburetor. This is a cross section of the fuel control unit where the mixture and throttle controls are. Here's the splitter. Once again, we've got fuel coming in from the fuel injection system, which is metered. It's going out to the fuel injectors, of which there is 1 per cylinder. So if you have a 4-cylinder engine, there's 4 of them. If you have a 6-cylinder engine, there's 6 of them. Plus 1 extra line going to a meter that's up in the cockpit, so you can see how much fuel is flowing. Here's what those meters can actually look like. There's a wide variety of them. They are often labeled with percent cruise power, which gives you a really accurate indication of how much fuel is flowing. So in summary, on this type of fuel injection system, it senses impact and venturi air pressures using a set of diaphragms to compare these pressures with fuel pressures to provide a regulated fuel pressure to the injectors. And it injects a constant flow of fuel right next to the intake valve. The mixture control restricts the fuel flow to the main metering jet and throttle fuel valve in order to lean the mixture. Starting on this one, I'm going to go with the starting procedure here that HAA has for their 172S model. Your procedure may vary, so again, study your POH. Normal starting, I'm going to skip to the part where we're actually starting the engine here. Step number 4 on the checklist is mixture to idle cutoff. And so this is really important. We want to shut the mixture off because that shuts the fuel off entirely to the system. We don't want to flood it when we turn the system on. We open the throttle a 1/4 inch, so now the throttle fuel valve is slightly open. The mixture valve is shut. The flashing beacon, we turn that on if it's not all the way on. We clear the area, turn the master on, and then we turn the aux pump on. And when we do that, if the fuel valves are open, fuel will immediately begin to flow out of the injector nozzles. But in this case, we still have the mixture at idle cutoff, so nothing's going to happen yet. But our next step is that we go mixture rich for 3 to 5 seconds. When we do that, fuel starts flowing up through the injectors and we prime the engine with a bunch of fuel right there at the cylinders. Then we bring it back to idle cutoff. ICO stands for idle cutoff. And that stops the fuel again. So all we've done so far is just prime the engine. Then we turn the aux pump off and we hit the starter. So we turn the key all the way to the start position. Now when we do that, we have our hand on the mixture instead of the throttle. But we're ready to immediately move our hand from the mixture to the throttle as soon as it starts. So we turn it to start. As soon as the engine fires, we move the mixture to full rich, move our hand over to the throttle, and we adjust the RPM to about 1,000 RPM. Common mistake on this one is to have the throttle too far open, set too far open, and since your hand's not on it when it starts, you go to a really high RPM right away, which of course is hard on the engine because there's no oil up in there yet. So be sure to not set the throttle open more than 1/4 of an inch. If you're not sure how to do that accurately, ask me in class and I'll demonstrate for you on one of the aircraft in the hangar. And then, of course, check your oil pressure. And once you know everything's running and everything's working, then go ahead and ground lean in order to keep the plugs from fouling. The other type of injection system is the Teledyne Continental, and this uses a very different approach. Instead of sensing air pressures, it senses engine RPM via a very special fuel pump. So that does not have any air sensing, none of those chambers on this one. It senses RPM by a special engine-driven fuel pump that's set up to provide more fuel pressure the faster the engine is turning. The throttle and mixture settings determine the fuel pressure to the injector nozzle. So here's a diagram of that out of your book. This system brings fuel in from the fuel tank and immediately puts it in a swirl chamber. That's what this little cylinder here is. The reason they do that is this system is very sensitive to air bubbles, and they want to remove all the air bubbles out of the fuel as it goes into the system here. And then they take that fuel and they run it back to the fuel tank. One really important thing about this system, as well as several other systems, including some pressure carburetors I've seen, is it sends some fuel back to the fuel tank. You need to know which fuel tank it is so that you can use fuel out of that one first, because if you use fuel out of a different fuel tank, you'll end up dumping fuel overboard because it's going back to a tank that's already full. Usually we send it back to the left fuel tank as sort of the tradition. So once the air vapor has been removed, the fuel goes over to the fuel control unit, and we have a valve here that is a mixture control, and this is not a restrictor valve, this is actually a selector valve. So the more you lean the fuel or lean the mixture, the more fuel gets sent back to the swirl chamber. The more you enrich in it, the more it goes on in through the system. And that's an important point that we'll come back to later. And then we have a throttle fuel valve that is directly mechanically linked to the throttle body. So as we open the throttle, more fuel gets sent up. And then it goes to a splitter just like the other fuel injection system, and just like the other one, we can tap off of it with a fuel pressure gauge. We can even label that in gallons or pounds per hour if we want to. A summary of this type of system is that it senses engine RPM using an engine-driven pump. It incorporates a fuel chamber to remove vapor, which is again an important point. It's got a mixture control that directs some fuel back to the swirl chamber, again an important point. And then it's got a throttle that controls both the fuel valve and the air valve. Altogether, it provides a regulated pressure to the injectors via a manifold. So starting on this one, under normal conditions is really straightforward because it's not going to start randomly blasting a bunch of fuel in there unless you really make an effort to do so. So you start it with just the throttle cracked, mixture full rich, master on, boost pump on, wait for an indication of flow, turn it to start, boost pump off, and you're done. Now, on a hot day, these can be a bugger to start. And if you want to be a hero, know how to do this. You'll help somebody out on a ramp someday. There's a really cool trick, and it works super good. I've done this a bunch of times. If it's hot, everything the same as normal, except first, you're going to go mixture idle cutoff, throttle wide open, and turn the master on. Then you're going to turn the boost pump on high for 15 to 20 seconds, which is going to seem like forever with that fuel pump making a racket. The reason we do this is that when fuel injection systems sit there on a hot engine, the fuel in the lines going out to the injectors and the lines that are around the swirl chamber and all that stuff, they get hot enough to boil the fuel, so there's little bubbles of vapor in there. So by leaving the mixture to idle cutoff and the throttle wide open, what we're doing is we're circulating a bunch of fuel back through the swirl chamber and removing all of the air bubbles. And it takes about 15 to 20 seconds to get all the fuel cycled through there and get all the bubbles out. You do that, turn the boost pump off, and then go back to the normal start checklist, and it will just crank right up. It's like a miraculous procedure that is right in the pilot operating handbook, but people hardly ever know it's there, including owners of these aircraft, and it's a really important little trick to know. Are you going to remember it after today? Probably not, but just remember it's there so that if you ever get in one of these aircraft, you can make a point of getting in there and learning that little point. Really great example of why it's important to know your aircraft. That's it for pressure carburetors and fuel injection. We will see you in class to talk about how these things fail and what we do next as pilots.